Hey everybody. So this should look familiar, and if my voice is warbling, I'm quickly losing my voice. This is the best I can do. So this is we're going to be talking about pH curves today, and probably I don't know who the sub's going to be, so you're just going to be watching this video instead of the sub teaching. So the sub is literally just going to start this video, and you're going to listen, and you're going to fill in your notepad, and it's like I'm standing here teaching to you. But psych, I'm actually in the back of the classroom. Turn around right now. See that bin back there? I'm actually hiding in it. Okay, who's looking at the back of the classroom? Yeah, you're dumb. Okay, so let's take a look at pH curves right now. So why do we have graphs? Well, acid-base pH curves are used in the real world to determine an endpoint. Now, this is where I'd probably tell you a story about being a lifeguard, but when I was a lifeguard, we had to check the pool chemistry. We had to take, every hour, we had to scoop pool water and test it for, test the pH and the alkalinity and dissolved minerals. So there's like 3 different tests. Oh, and the chlorine. So there's 4 different tests that we ran, and we had to do like little mini titrations. Somebody had already done the titration before to figure out when there was a color change, about how much chemical is mixed. So the reason why those graphs are important is then when you graph it out, you can then apply that to things like a lifeguard in a swimming pool. And graphs visually, coronavirus, visually show what type of reaction is taking place. All right. So you need to know more than what you were taught in Chemistry 20. But the good thing is that we usually teach way more in Chemistry 20 than you're supposed to know. So if you had me as your cohort teacher, we did lots on pH curves. Now, the reason why pH curves work the way they do is that you kind of have to look at the title. And the title of this says we have 25 mils of 0.48 mole liter sodium hydroxide titrated with hydrochloric acid. So the width part is important. The width means that's in the burette. So the burette is that, I know some of you guys have never used a burette because of coronavirus. So the burette is the tall, skinny thing, and you have an abundance of hydrochloric acid. And down here, you have sodium hydroxide. Now, wait a second while you guys draw anything you want to draw. I don't know if you want to draw that. Okay, you've drawn it. That's great. The good thing is the sub can just rewind this. I'll post it on Google Classroom too, so you really don't even have to be in school. Actually, why did I say that? Cut that. Oh, I can't edit this. Okay, whatever. But so when you take the pH first of the solution, you stick what's the pH in here? Well, it's going to have a wicked high pH. So like if let's say we put some numbers on there, 7, 1, 14, like our first pH point is going to be really high. Now, okay, that's going to get in the way there. We're just going to move that down. And as we slowly add hydrochloric acid to this, the pH doesn't change for a while. And you probably saw this. That is a big chunky dot. You probably saw this in Chemistry 20 until all of a sudden there's a change in pH. So you get this curve going on. Whoa. That's the pH curve that you guys would have been shown in Chemistry 20. Now, the front part where there's not any change, that's called the buffer zone. Where there is, like about the middle, is called the end point. At the end point, we also have something called the equivalence point. Now, that's super important. At the equivalence point, the mid-range of the drop, the moles of acid and base are equal. There's an equal concentration of moles. So at position 1, we have way more hydroxide than we do hydronium because it's buffering. But at position 2 here at the end point, we have an equal amount of hydroxide and hydronium. Okay. Now I call this endpoint, not this endpoint, I call this area of the graph down here. This is Steve. Never ever label the end of a pH curve. It actually doesn't have a name. So we're just going to call it Steve. Right. So, oh yeah, this is look, this is a mess. What was going on here? Oh yeah, all right. Okay. This is going to be fun for the kids at home. Look at all these. Okay, you go over there. Whoa, not you. You don't belong. Okay. So one of the reasons why, let's get some more in there. Nope, not you. Nobody likes you. There. Okay, get some more. Okay, this is wasting time. One of the reasons why there's a buffer zone is that if you take the pH here, there's just so much hydroxide. And then as the, oh, that's kind of cool. I clone that. As the H3O, let's make this bigger. Whoa, that's a big H3O. As that comes down through the burette, it will touch one of the hydroxides, and take it away, right? Neutralize it. But there's still so much hydroxide left, so the pH doesn't change. Oh, here comes another one. Oh, Okay, this comes another one. Okay, takes away. So even though we've added now a bunch of hydronium, the substance that's left, like we still have so much hydroxide, we still have a wicked high pH. The pH maybe hasn't changed until, we get to the last one. And now when this goes down, that will neutralize it. And now there's no hydroxide left. And we have this rapid change in pH. Pow. pH curve. Okay. So remember, the buffer zone is the front of a pH curve. Now, there are other acids that have multiple buffer zones. And as long as there's some hydroxide ions present, they buffer or they react with the hydronium ions from the acid and neutralize, thus not affecting the pH. So as long as you, like when you're buffering, you're still going to have stuff left over. Okay. So if you see strong acid titrated with strong base, that means you start with strong acid. Oh, you start with, whoa, what's going on here? Okay. It already says that. That means you start with a bunch of acid and are adding base slowly to it. So the idea in Chem 30 is you have to be able to predict the shape of many different pH curves. So if we were adding strong acid, if we had strong acid titrated with strong base, that means we have lots of acid to start with. So is that on the next slide? I forgot. Nope. Okay. We'll do a mini one right here. So we have pH. And what are we adding? Strong base. Right? So let's put our, 1, 7, 14. So we have lots of strong acid. Before we add any base, its pH is going to be low. And over time, no change. Then rapid change. So this gives us the opposite pH curve of the last one. The idea is that strong via strong have this characteristic S shape. Like that or like that. All right, what if we had a weak base titrated with a strong acid? Okay, let's set up our y-axis, pH, 1, 7, 14. What are we adding? Strong acid. Okay, so what do we start with? Weak base. Well, where would the pH of a weak base be? Before we add any acid, like around there, right? Now, I'm going to use a martial arts example. I've been doing Kung Fu for 14 years. And one of the things that happens is when people come to Kung Fu for the first time, no matter who they are, unless they have had experience of being in real fights, nobody knows how to fight. They're scared of hurting people when we put gear on. And one of my favorite things to do is to let people punch me. I love it. I kind of turtle up and I was like, yeah, punch me, kick me, because I've got gear on, right? So that's one of my roles. I love doing it. I'm a big guy, right? Like, obviously, you're not supposed to punch and kick people when you're sparring as hard as you possibly can. But if you punch somebody, even like, 40%, somebody really strong, you're not really going to get hurt. It doesn't really hurt me. So, but the thing is when we're actually supposed to spar, when I'm done helping them out, and I'm like, okay, it's time to do what you have learned, have time to do what you have been taught. Let's see how you do against somebody experienced. Somebody who is not very experienced doesn't last very long in a sparring match. Now, of course, sparring match has rules. Sometimes in martial arts tournaments, there's a whole bunch of rules. In Kung Fu, we have all of these different moves where we kick people in the groin, but you're not supposed to do that when you're sparring, so we don't, because it kind of hurts. But the idea is that if you start with a weak base, that's like somebody who's a weak fighter. Are they going to last very long against somebody who's a strong fighter or somebody who has lots of experience? Probably not. So the buffer zone is really over really quickly. Okay, now I drew that a little too fast. We'll back up a bit and we'll put the dots in there. So it's like, oh no, I'm fighting somebody who's stronger than me and they know more Kung Fu or martial arts. And it doesn't matter, any martial arts, right? Okay, it's like, oh, they dance around for a bit and then it's over. Nobody gets hurt when you spar. If you hurt somebody when you're sparring, you're a jerk. So this is just like you win the match. All right, so we have a short buffer zone. I might lose my voice completely. Okay. And our endpoint is below 7. Okay, enough of that. Moving on. What about a weak acid titrated with a weak base? Okay, that's like 2 people who've just started Kung Fu or karate or any other martial arts, if you take it, who are sparring against each other. They're trying their best, but the match usually goes forever because they don't know what they're doing. You can never score a clear point. Okay, that's in point sparring. Point sparring is kind of stupid. But even in like continuous sparring, there's a lot of like dancing around and little wimpy kicks. And I was there once. I was terrible at it. Okay, what are we doing here? So weak acid titrated with weak base. So weak base, we have starting with a weak acid. So, and we're adding weak base to it. So about there, right? So because you have such a weak acid and a weak base interacting, the buffer zone is really kind of nebulous. It might look like that. We don't have a nice buffer zone. All right, so that's a weak acid titrated with a weak base. Undefined buffer zone, undefined, like where's the endpoint? I don't know. Okay, what's next? Oh, yes. Okay, polyprotic substance. Now, so we're going to review this. This is chemistry 20, and we're going to do the Bronson-Lowry reaction for a substance that's polyprotic. So I don't know how long I've been talking for, but this is important. I'm going to take time to do it. So if you remember in Bronson-Lowry, when you have a strong acid, what do you write? Well, you don't write hydrochloric acid in your entity list. You write H3O positive and the chloride ion, the conjugate base of hydrochloric acid. Now, sodium hydrogen carbonate, we're going to break apart the sodium and the carbonate ion. And what's always hanging around, what's always there? Did anybody say water? Everybody say water. Oh, we're all together as one. Water, right? Water. H2O, you know. It's in you. Okay. So our strongest acid, I've got this memorized. You can fact check me later if you want, but I'm pretty sure the strongest acid in this list is the hydronium. The strongest base, if you put your finger on hydroxide and you work your way up on the right-hand side, is the carbonate ion. So those two are going to react. Now, there's actually two possible reactions here because it says to completion. Basically, that means we have an unlimited amount of hydrochloric acid, and we're going to keep adding it until there's no more base left. So the first reaction is pretty straightforward. Hydronium plus the carbonate ion. Acids give away a hydrogen. Okay, we get HCO3 and water. Okay, now if we check our table, this is products favored. The acid is above the base. An interesting thing happens when you have, like if a question says to completion, you have a second reaction that occurs. Because instead of saying this is used up and it's gone, what this means is like you have an unlimited supply of it. It's still there. You have a finite supply. You can't see me pointing. You have a finite supply of that. So what happens is this reaction occurs. And this substance right here, the hydrogen carbonate ion, it is now going to be our base in the second reaction. So we have lots and lots of H3O. And it will react again because it's still a base. Once all of the carbonate ion is gone, carbonate ion is like first choice. I'm sure you guys have all been somewhere where there's like treats or some kind of food. The first choice is whatever, okay? I don't know, Timbits, right? Everybody eat Timbits? What's everybody's favorite Timbit? Okay, you got 10 seconds to talk to somebody beside you right now about what the best flavor Timbit is. Now, there is one right answer. Everybody listening, there's one right answer. You talk to somebody for 10 seconds, go. I will wait. This is more important than chemistry. Okay, did you talk to people about Timbits? The correct answer is sour cream glazed. Oh, no, I don't want to hear any. No, stop that. Who's that? Quiet you. It's sour cream glazed. That is the only right answer. You're all wrong who didn't pick sour cream glazed. If you pick something weird like a honey cruller, that's the worst. Just leave now. Actually, don't leave. That's illegal. Okay, continuing. So first choice is the carbonate ion. But once it's gone, like first choice is sour cream glazed Timbit. Second choice for me probably is, I don't know, I really like the chocolate sometimes. It's a little bit much, but I'd say chocolate is second choice. The hydrogen carbonate ion is our second choice. It's still a base. It's one of those amphiprotic ones. It can act as a base. And the hydronium continues to react because we have so much of it. Now, this was something, if you did online learning, I definitely rushed through. But the idea is there's always multiple reactions when you have acids that are called polyprotic acids or polybasic bases. A polyprotic acid has the ability to give away more than one hydrogen. A polyprotic base means it has the ability to accept more than one hydrogen. Now, you can find these on your table. I'm just going to finish this, and then we'll talk about that in a second. The net reaction looks like this. It's everything that's on the reactant side, I add up together. And everything on the product side, I add up together. But entities that are the same on either side are canceled out because they actually are not in the net anymore. So this and this, both of those, they are eliminated because they're the same on either side. Okay, and we have two hydroniums and a carbonate ion. On this side, we have two waters and carbonic acid. Okay. All right, back to polyprotic substances. And it's kind of running out of room here. So, polyprotic acids if you're not sure, you can check your table. For example, HOOCCOOH. Is that polyprotic? Polyprotic means it could give away 2 hydrogens. Not every acid with 2 hydrogens in it is polyprotic. So you check your table, and guess what? Okay, that's oxalic acid. It gives away 1 hydrogen. Then you take your finger. This is called, right, slidey finger. You slidey finger. Then what you do is you move your finger. This is called movie finger. And look for that substance below. Okay? So this substance, we're going to look to see if it acts again as an acid. You go down the table, and guess what? You'll find it on the table giving away another hydrogen to become this OCU thing. OCU. Okay? So that's how you tell if something is polyprotic. There's evidence on the table that it could give away more than 1 hydrogen. The same is true for a substance that's polybasic. Polybasic substances are a little bit trickier. Usually, they're like this example. They've got a metal attached, so you got to get rid of the metal. The carbonate ion is a good example. The carbonate ion is 2 negative. So that gives me a hint that it could possibly take 2 hydrogens. So what we do is we follow it back. We say, okay, can it gain a hydrogen, right? Can it gain a hydrogen? The answer is yes, it can. So that's called slidey finger. Then you move your finger up until you find it again on the table, gaining another hydrogen. So there's evidence that it moves, or like it can give away or take more than 1 hydrogen. And the cool thing is that you make this Z pattern to figure it out. So I am trademarking this as slidey finger and movie finger because you know what? It makes the first letter of my last name. That's not true. Okay, so let's move on. So if we have sodium carbonate reacting to completion with hydrochloric acid, this is the shape. You should have got this from Chem 20, but we'll review it. So sodium hydrogen carbonate is a weak base. The only strong base is anything with hydroxide. So we have, starting with sodium hydrogen carbonate, okay, so it starts there, and we've got hydrochloric acid. And we have a buffer zone and then a change. That represents this reaction, reaction number 1. So right here, we have the carbonate ion in greater concentration than the hydronium ion. At this point, we now have the carbonate ion equal to the hydronium ion. And then guess what? It's gone. But the hydrogen carbonate picks up the job, and it has a buffer zone as well. So now we have the hydrogen carbonate ion in greater concentration than the hydronium ion, but it changes as well. And then now we have the hydrogen carbonate ion in the same concentration as the hydronium ion. And then at the bottom we have Steve. So you get this double bump graph. So polyprotic substances, if there's evidence that they can give away hydrogens multiple times or take hydrogens multiple times, you have a double bumped graph. Now, one of the interesting things that you can do in all of these graphs is wherever the endpoint is, wherever the big change is, the endpoint, okay? Wherever the endpoint is, you can pick an indicator that will let you know you've reached the endpoint. There should be a color change at the endpoint you picked. Okay. So, for example, let's say the endpoint here is, 3. What indicator would you pick that would have a pH of 3? Well, everybody get your data booklet out to the indicator table. Okay, I've got mine. So we look in our for a pH range that has 3 in the middle of the range. Oh, I screwed up. Okay, there's nothing with 3 in the middle. Okay, let's say this is 4. Yeah, that works. Okay, so let's say that's 4, not 3. Okay, do we see something that's got 4 in the middle of the range? Now, we could say we could use methyl orange. Because methyl orange's range is 3.2 to 4.4. So 4 is kind of in the middle. And what we'll see as we get close to that point, methyl orange, when it is basic, looks like it's yellow. So it's going to be yellow all the way up here. And then below 3 is going to be red. Because that's its range. It's red, and then it's yellow. So what color does red and yellow make? Well, kind of orange. So we'll know we're at our endpoint at pH 4 because orange is a mix of the two different endpoint colors. Okay. Last question. Carbonic acid reacts with sodium hydroxide. All right, so carbonic acid is H2CO3, okay, and hydronium, and hydroxide, sodium ion, and water. Okay. Is carbonic acid a polyprotic acid? Because that's going to change the graph. Now, I'm suspicious that it's polyprotic because guess what? It's got 2 hydrogens showing. So I find carbonic acid in my table. It's kind of at the bottom. It's not a great acid. And I slide my finger over. Okay, it becomes HCO3 1 negative. Then I move my finger down in a Z pattern to see if HCO3 is there again, and it is. So this substance is polyprotic. It can give away 2 hydrogens. So when we draw our graph, okay, the width part is sodium hydroxide, so carbonic acid starts there. It's kind of a weak acid, maybe middle. We will see 1 hydrogen changing and another hydrogen changing. 2 buffer zones, 2 endpoints. BZ stands for buffer zone. Okay. So what's tricky on the diploma is they could pick like here and then ask you a question about like what's going on right there. What's happening there? Well, that's our second endpoint. All right. Now it could say what's the reaction that's happening there, or like what's going on right there. Well, here we have H2CO3. But from here on out, H2CO3 is gone and we have HCO3. So what's happening at endpoint? Endpoint, remember, is where things are equal. We have an equal amount of the hydrogen carbonate and the hydroxide ion. Okay. That's good for today. There'll be some extra information your sub will give you.